Hello, Physics 1 students. Let's get started here with the last problem in our problem set, number 13. Go ahead and read it, do all of part A, then go back to see how I do it. Okay, so you probably want a periodic table in front of you in case you don't remember what polonium is. It's not one of the standard elements that you're quite used to. Symbol is PO, and it's emission of alpha particles, so it's an alpha decay, and it does ask you to include all the electrons, so it should look something like this. So it's polonium-210, polonium is element number 84, of course there's 84 electrons, here's our alpha particle with its 2 electrons, and by conservation of charge, 84 here, 2 there, leaves 82 here, which is element 82, which is lead, or plumbum in the Latin. Conservation of mass number is 210 here, 4 there, leaves 206 for this, and of course here's the associated 82 electrons with lead. So there's all of part A, nice and simple. Alright. Let's go on to part B. This is a little more interesting. Okay, so polonium was at rest before decaying. The two resulting nuclei, that would be in this case the helium and the lead, push off each other, sharing the energy released from the reaction. We want to find their speeds. So the first thing we want to do is, of course, find the energy released. This is the time to use delta E equals delta MC squared, so it's going to be the difference in masses. We're always going to do this in terms of sort of like an absolute value, so it's the larger minus the smaller. I know it's not exactly right, but this way we won't have to worry about a negative change in energy. That might be a little bit confusing. So it's the difference in the mass of the original nucleus and the resulting nuclei. We remember when we look up the numbers on the chart, the numbers of the mass, atomic masses already include the masses of the electrons. You don't have to worry about that. So once you pause the video here, go ahead and put your numbers in. Let's go ahead and calculate delta E. Okay, so of course you're looking at the chart in the appendix here. Polonium is down here, it's polonium-210, so we're using this value here. Lead-206 is this one over here. You got to make sure you're using the right isotope. Remember, we're always using the numbers from this column here of atomic mass. So it should look something like this. Again, I hope you're not just copying this down and writing down what I have. You really need to go through the process yourself of finding those numbers on the chart and faithfully copying those numbers down. It's not easy. It's a little bit tedious. I totally understand that. Just a minor point here, I just want to go back and remind ourselves we're not doing the idea of binding energy or adding up the protons and neutrons to form the nuclei. These nuclei are already formed. I know that's where a lot of students get confused. There's two major types of times that we use this equation. One is when we want to find the binding energy of a nucleus. That's when we're putting together the protons and neutrons to form the nucleus. The other time is in an actual nuclear reaction where we already have the nuclei and we're finding the difference in masses from start to finish. Let's remember, we're going to use our 931.5 mega electron volts per c squared per u conversion factor. We use this so that it gets rid of c squared. We don't have to ever multiply by c squared. Gets rid of all of our units of u, atomic mass units. And when we carefully put all the numbers in, we should be getting 5.407 mega electron volts. But that's not the end. That's just finding the energy released in the reaction, which is then shared between the two resulting nuclei. We have to find how fast they're moving. Okay, well, what sort of energy do they have when they're moving? It's got to be kinetic energy. So this 5.47 mega electron volts is the kinetic energy of both nuclei. So it's kinetic energy of the alpha and the kinetic energy of the lead. And here I changed the subscript to alpha. You want to keep it as helium, that's fine. Or you want to call them like Ke1 and Ke2. It's totally up to you. But there's two particles here, the helium nucleus and the lead nucleus. They push off each other and they share this kinetic energy. This is the energy released in the reaction from the difference in mass. But they do push off each other. That should sound familiar. What sort of problem is that where objects push off each other? They start at rest, they push off each other. That's an explosion. What do we do when there's an explosion? Oh, that's going to be conservation of momentum. So here we have an energy approach, and we're also going to have a momentum approach. But just, so we get some equations in here, we can replace both these kinetic energy equations with 1/2 mv squared. We're kind of using the alpha notation, or you want to call m1 v1 squared, m2 v2 squared. That's all fine. Here's our conservation of momentum. From here on out, it really just becomes a bit of a complicated algebra problem because we're going to solve this for one speed or the other. So, for example, we can solve it for the velocity of the lead or the velocity of the alpha particle, and then you're going to put this mess into here and collect terms. And if you want to do it, it's totally up to you. I encourage you to do it. It's a complicated problem, and one of the most complicated parts of it is not just the algebra, but also keeping track of your units, which is what I told you one of the major hurdles is of this topic, right? Because this is in mega electron volts, and we're dealing with energy and momentum, we have to convert it into joules, right? So you have to use a conversion factor there. Also remember, it is mega electron volts, not just electron volts. Mega is the factor of 10 to the 6th. You have to worry about that conversion. The masses, well, they can't be left in atomic mass units. They have to be converted into kilograms. You have to use that conversion factor. So there's a lot going on here. I'm going to give you the answers, and I encourage you to try the problem on your own, although, it is a lot of algebra and a lot of calculations, but it's certainly not something you can't handle. And so here are the correct answers. The speed of the alpha particle, 1.58 times 10 to the 7th meters per second. The speed of the lead nucleus, 3.07 times 10 to the 5th meters per second. And even if you don't want to go through the whole process here, do these numbers make sense? Well, if they're pushing off each other, we see that the alpha particle, which has a lot less mass, is going much faster, and the lead particle, which has a lot more mass, is only going a lot slower. It's still going really, really fast, but it's going a lot slower. So at least the numbers qualitatively make sense. Okay, let's go back into our concepts, and the second page there had this question here, where you're going to categorize your equations. We've done this sort of thing before, but I told you this is the other major hurdle in this topic, is knowing when equations refer to particles of matter, when they refer to particles of light, or maybe there's some all-purpose equations. And you can use, abbreviations, P for photon, M for matter, B for both if you'd like to, but pause the video, answer this question on your own. Okay, so let's start with all-purpose equations. Which equations here deal with everything, matter and light? Well, one of them is this one here, right here, letter H. Since this is just P for momentum, and we know that, of course, objects have momentum, and light now has momentum, this is an all-purpose equation. This works for both situations. And there's only one other equation that deals with both, and that's here, letter B, because Ke is, of course, the energy of an electron, and HF refers to the energy of a photon. So in this case, it's an all-purpose equation. It refers to both matter and particles of light. So if you had anything else that refers to everything, that's incorrect. Maybe you want to pause and try again. Okay, let's go to just photon equations. And notice I've left some of the subscripts off on here on purpose. So hopefully you recognize that letter C is normally E photon. That's the way I write it, and that's the way I'd like you to write it every single time. This is the way you may see it in the textbook, but I write it that way to remind myself it's only the energy of a photon, which makes sense because we're talking about frequency, and objects don't have frequency. By the same token, I always write this as E photon equals PC, and a good clue here is that involves c, the speed of light. So of course this is the energy of a photon, a particle of light. And that's it. Everything else refers to matter. Kinetic energy, well, photons don't have kinetic energy, they don't have mass. They have energy, but they don't have kinetic energy. This is the stopping potential to stop those electrons. Over here, remember, this is the energy of an electron in the nth energy level, specifically of hydrogen. Remember, this equation only works for hydrogen. Clearly, F and G are for objects because it deals with mass, and that was also why in letter I this is for an object with mass, because it has the mass in the equation, right? That's why these two equations are, a little bit different. This is the all-purpose equation for either matter or for light. This is this equation that's specifically for objects with mass because it has the mass in it. And like I said, it's so important to know which of these equations are for which situations.